Next, let's look at a really famous algorithm called longest common subsequence. There's a lot of dynamic programming problems that fit this exact same pattern. Like, you would be surprised how similar they are and how many different variations there are of this problem. And the prompt is pretty basic. We're given two strings, S1 and S2, and we want to find the longest common subsequence between these two strings. First of all, what even is a subsequence? Well, it's basically a subset of the characters of a particular string. So a subsequence of this string could be the string itself, or we could remove some character. So this would be a subsequence. It doesn't have to be contiguous. So the difference between a subsequence and like a subarray is that it's not necessarily contiguous. For example, these two characters together are also a subsequence of S2. But the thing about a subsequence is that the relative order does have to be maintained. So for example, here AC is a subsequence of S2, but we can't say that CA is a subsequence. It's a subset of these characters, but it's not a subsequence because the order does matter when we're talking about subsequences. That's the difference between a subset and a subsequence. So in this case, the longest common subsequence between these characters is a subsequence from both strings that is equal. So in this case, the longest subsequence would be AC because both of these strings have that subsequence. It's unfortunate that we can't take ACB to be the subsequence because the order is not matching. The C and B are in, a reverse order. So the longest we can get is AC. Even though we have like a potential hole over here, that's perfectly fine. And actually, it would be fine if we had like a D over here and we had a C over here. We would have a matching A, and then we would see, well, there's no matching D and B, and over here, this D won't match either, but the C from over here will match this C. They don't necessarily have to be in the same position either for, a common subsequence. That's the idea here. Now, there are some dynamic programming problems like this one where if you can even figure out the brute force DFS solution, the recursive solution, you can actually come up with the optimized solution relatively easy. But even coming up with a brute force can be kind of tricky. But once you know it, you can apply this pattern that we're going to talk about to any of the problems that fit under this umbrella. There's quite a few. So if you're just looking at this problem, trying to think of what the solution might be, your brain might be going blank, and that's perfectly okay. That's how I approached this problem the first time I saw it. But we know at the very least, we're going to have to compare characters between the two strings. I don't think there's any possible solution that we could avoid doing that. So let's start by initializing a pointer at the beginning of each of these strings. I'm going to have one pointer I1 and another pointer I2. Basically by pointer, I mean index. So starting at the beginning of the two strings, one possibility would be that the strings themselves are equal to each other, right? Because that technically counts as a subsequence, having equal strings. So why not start by comparing character by character? So between the first two characters, these characters are equal. So we know at the very least, we're going to have a subsequence, a common subsequence of length 1 at the very least. So if we know that, what becomes our subproblem? So if we know that, then we can take our pointers and then shift them by 1. So I1 can be over here and I2 can be over here. We know if these characters are common, then there's no need to do anything else with them. Then we only have to compare the remainder of the two strings. So do you kind of see what the subproblem is now? We originally were given two strings S1 and S2. If we see that the first characters are equal to each other, then we know that now the solution becomes 1 plus the LCS, the longest common subsequence, of the remainder of the two strings. So S1 starting from index 1 and S2 starting from index 1 as well. So to represent that with a decision tree, this is what we would do. We would have initialized our I1 and I2 to 0, and if the characters are equal, we actually just have one decision. We don't need to consider any other possibilities because the characters were already equal. We know the LCS of two equal characters is just going to be the characters themselves. So I guess you could say that the next decision that we made or the next subproblem that we were trying to solve is where I1 is equal to 1, and I2 is also equal to 1. This is where things are going to get interesting though. Now we reach the more complicated case where the two characters are not equal to each other. So what should we do now? We know we have to try to find at least some common characters. Just from looking at the drawing, we can see that there are some common characters, but we're going to have to probably increment our pointers to do that. We see that C's are common, but we also see that B's are common as well. So we don't necessarily know which one is going to result in the longest common subsequence. But we know at the very least that both of these two characters cannot be included in the longest common subsequence. How do we know that? Well, it's sort of a proof by contradiction. We see that obviously these two are not equal. So if we want to find a common character between these two strings, we have to shift one of these pointers. We can leave, maybe we can find a B character, in which case we would take I1 and shift it and try to eventually find a B character so that this character could match with a different character. Or we could do the opposite thing where we keep our I1 pointer over here, but we try to take our I2 pointer and then increment it and try to find something maybe that matches with the D, but we won't be able to match these two together because remember, the order of the subsequence matters. We have to take one of these pointers and increment them at the very least. Maybe we'll have to increment both of them. We don't know for sure, but we know at least we have to increment one of them to find a matching character. And because we don't know which one to increment that's going to result in the longest common subsequence, we try both possibilities. So we try the subproblem where we increment I1, which would mean I1 is going to be set to 2 and I2 is going to be set to 1. We try the other subproblem where I1 is set to 1, it stays as 1, and I2 is set to 2. This subproblem would be incrementing I1. So we're trying to now find the LCS between these two substrings. We skipped this character over here, but we're trying to find the LCS of the remaining portion of these two. The right branch over here would be we left I1 where it is, and now we incremented I2, so we skipped this character and we're trying to find the LCS of these two strings. And actually in this case, the LCS of both of these subproblems is going to be equal. So both of these will actually result in the longest common subsequence. But let's run through the logic quickly. For the first choice, we had these two substrings remaining. So here we would check that B and C are not equal to each other. So once again, we're going to have two branches where we increment I1 and set it to be 3 now, and I2 will stay the same. Or we have the other branch where I1 stays the same and I2 is going to be incremented to be equal to 2. So this left branch would be where I1 is now at 3. So it would be this substring. We skipped both of these characters and we would still have this as our S2 substring. And at this point, we would see that B's are equal to each other. So then we would increment the pointer here. We would increment both pointers actually. So I1 would be equal to 4. I2 would be equal to 2. So what that means is that we're basically over here now, right? Our I1 pointer is out of bounds, but our I2 pointer is pointing at this character. If one of these are out of bounds, this is the new subproblem essentially. What's the LCS between the string C and an empty string? Well, the empty string doesn't have any character, so probably the LCS is going to be 0. So that's our base case in this recursive algorithm. If one of the two substrings is empty, aka we have reached the end of one of them, then the LCS is going to be 0. Maybe we'll reach the end of both of them. That would only occur though if both of the substrings were equal, because if we were comparing maybe AB and AB, we're trying to find the LCS of these two strings, we would see that both of the strings are equal. Both of our pointers would reach the end of both of the strings at the same time. This is just kind of the thought process behind this solution. But going down this path, what we actually found was these two matching pairs. We found this matching character and this matching character. And if you recall, the first pair over here was where we got that 1 from. And when we did that, we were basically saying, remember, if we find one matching character, then our result is going to be 1 plus the result of this subproblem. And then when we got to this subproblem, we didn't find any matching characters immediately, but from here we went down to here, and then here we did find matching characters. We said that the result is going to be 1 plus the result of this, and this was our base case, so this returned 0. So when we pop all the way back up to our root, we counted 1, 2 as our result. So that's the longest common subsequence. Well, the length of it at least, and that's what we cared about in this problem. We care about the length. We don't actually care about building the subsequence itself. Now let's quickly try to explore more of the tree before we move on to the code. This time, let's go down this path over here. Oh, I just realized we talked about how these two characters were matching, but when we went down this path, it was actually the B's that were matching over here, and then we ended up going out of bounds on this side. Sorry about the confusion. It's this path over here that's going to have the matching C's, as I'm about to show you, because both of our pointers are at the second index. So that would mean we're comparing this character with this character. If they are both equal, then we shift both of the pointers by 1, and we basically say our result is going to be 1 plus the LCS between the remainder of the two strings. We have a B in the first string, but the second string is empty. So that would essentially be our base case. So that's what this path would end up, resulting in. And that ends up giving us the same length. So we get an LCS of 2 from this and this, whereas on the left side we actually got the same length for the LCS, but there were actually multiple results. So you can see that finding the LCS does not necessarily have a unique solution. It might have multiple solutions. And now let me show you something interesting on the right side over here. If our I1 is at index 1, that means it's at the D. If our I2 is at index 2, that means it's over here. These two are not equal to each other. So we can try incrementing I2. That would be the right path. So I1 stays as 1, I2 would be 3. But if I2 is 3, that means it's out of bounds. So this is basically a base case. We're going to return 0 from here. But going down the other path is going to be a bit more interesting, because in that case, we'll take I1 and increment it to be over here. So I1 would be over here. I2 would still be at index 2 over here. So again, we see that we get matching C's. That's what we also found going down the other path. So we would get to I1 equals 2 and I2 also equals 2, and we would be solving this subproblem. But you notice how we're solving the same subproblem in multiple places in this decision tree. This is kind of a hint at the repeated work that we have to cut down on, because you can see that in some cases we won't have 2 branches in this tree, but in the worst case we'll have 2 branches on every single position in this tree, meaning the worst case time complexity is going to be 2 to the power of some variable. What's the height of this tree going to be? What's the maximum possible height? Well, in the case where we're branching 2 times, we're only incrementing one of these 2 pointers. So how many total times can we increment these 2 pointers? Well, of course, it's going to be the total length of the 2 strings combined. So let's say the length of the first string is n and the length of the second string is m. We would say that the time complexity here is going to be 2 to the power of n plus m. That's going to be the time complexity. The memory complexity is going to be n plus m. That's because it's the height of the tree, and that's going to be the height of the recursive call stack. So now let's move on to the code. It's not super complicated, but admittedly, it would be difficult to come up with if this is your first time seeing this problem and this type of pattern. So this is the recursive solution, the most brute force solution. The code is not super complicated. We're given 2 strings, and we also have a helper function. The reason we have a helper function is so we can keep track of the indexes of each string. Instead of doing that, we could have actually passed a substring into each recursive call. So, for example, if our I pointer was over here, we could have passed this substring instead of passing the entire string, but that creates extra memory. So it's easier to just pass the index that we're at. So if we're at the beginning of each string, we would pass 0, 0. That's what the original problem is. And then we break it up into subproblems as we increment our pointers, of course. The base case, what we talked about, is when we reach the end of either of the strings. If that's the case, we know that the longest common subsequence is going to be 0. But if that's not the case, we know that there's 2 possibilities. These 2 characters are equal, in which case we would return 1. We're getting that 1 from these two characters being equal, because then the LCS becomes 1. At the very least, it's 1. And we add to it the LCS of the remainder of the two strings. We get that by taking I plus 1, moving it to the next position, and I2 plus 1, which is the second pointer, and moving it to the next position. So this becomes the subproblem. The overall result is going to be 1 plus the result of the subproblem. But if the two characters are not equal, which would occur when we get to the second position, then we don't know what the solution is. We don't even know if it includes this character or if it includes this character, or it might not include either of these characters. So what we do is we try shifting one of the pointers. So we try shifting I by 1 and seeing maybe the LCS of these two will give us the result. Or we try shifting the other pointer over here and say that maybe these two will give us the result. You might be thinking, what about the third case where we have to possibly shift both of the pointers and maybe these two will give us the result? Well, believe it or not, that case is already handled for us because of the way recursion works. For example, when we only shift the first pointer to this position over here, then we're going to compare these two characters. We're going to see that they're not equal. So what we're going to do is try shifting the first pointer, which would give us this subproblem, and we'll also try shifting the second pointer, which would give us this subproblem. So you can see that all possible subproblems are enumerated basically by just handling these two cases, because we know recursively those two cases are going to keep on running as long as we have unequal characters. So this is the idea, and you can see that which variables are changing. Another reason why instead of passing in substrings, we pass in indices is because we can see exactly what's changing here. We can see that we're moving to different positions of each string. We calculated that the size of the tree, the number of times this recursive function is going to run, is in the worst case 2 to the power of n plus m, because there might be a lot of repeated work in that tree, as I kind of talked about. But we know that all possible values that could be passed into this function, like all possible combinations that could be passed, well, we know the two strings are not changing, but we know the indices that we're at are changing. So all possibilities for I1 is basically the length of the first string, which is n. All possibilities for I2 is the length of the second string, which is m. Multiply those together gives us all possible combinations this could be called with. That's why we can apply caching to this input, because if we calculate the result of this function call once for a certain set of given parameters, maybe 0, 0, or maybe 0, 1, then we don't have to redo all the work, because redoing the work might mean recursive calls. So if we can eliminate that repeated work, then this can be our overall time complexity. Now, once you get pretty familiar with dynamic programming and memoization, you usually don't even need to think that far. Like what I just talked about, you don't always need to go through that entire thought process. But as a beginner, I would recommend thinking about it that way. But usually what I do is I just turn my brain off. I just write the DFS solution, the recursive solution. I see which variables are changing, and then I just apply caching to those variables. Usually it's 1 or 2 variables. 3 variables that are changing is pretty rare for dynamic programming. Those problems can get more difficult. Those are 3-dimensional dynamic programming problems. Usually 2 dimensions is enough. If you notice you have more than 2 dimensions, it might be that you're not calculating the brute force solution as efficiently as you could be. So now let's take a look at the caching solution. The good thing about memoization is you can kind of turn your brain off and just apply the same pattern that you usually do, which is create a cache that's of the size of the problem space. We talked about ours as n times m. So I'm basically creating a 2-dimensional array of that size, m columns and n rows in this case. This is how you do it in Python, but I think most languages you can actually do it more easily. And we call our memoization helper. We pass in the exact same parameters, but this time we're passing in the cache. So we have the same first base case. If we go out of bounds, then we're going to return 0. It's important to put this base case before you put the cache base case, because if we go out of bounds, we want to check that before we try indexing our 2-dimensional array, because we don't want an index out of bounds error when we try to access this 2-dimensional array. But if we're not out of bounds, then we're going to check, have we already computed the result and put it in our cache? We will know that because we initialized our cache with a -1. We know -1 is nonsensical in this case. The longest common subsequence between two strings can't be -1, so we know it's a pretty good default value to use here. So if the value here is not -1, that means we must have computed it already, in which case we would return that value. We don't need to do these recursive calls. But if we didn't compute it, then we do have to do the recursive calls, and we would handle them the exact same way we did with the DFS, passing in the same parameters, except this time we're passing in the cache, of course, into the recursive calls. But when we get the result, we're not immediately returning it. We're actually storing it in our cache so that next time we call this function with the exact same parameters, we don't have to do this work again. We can go straight to the value in our cache and then return that. And if I was doing this in a real interview, I would hope that this solution is enough for the interviewer. But if it's not, we pretty much have enough information here to go to the true dynamic programming solution. Because we know the size of our solution space, it's going to be a two-dimensional grid, the dimensions of the two strings. And most importantly, we have these two formulas here. We know when we reach two characters that are equal, the problem becomes 1 plus the subproblem where we increment both of the pointers. The other case is if the two characters are not equal, then we have to calculate the max of these two subproblems. These equations are the basis of the true dynamic programming solution that we're going to talk about. Though there can be a few more edge cases, which I think can be really confusing, that's why drawing out the grid is really helpful. That's what I'm going to show you. So we have our familiar two-dimensional grid once again. The dimensions, well, the rows are going to be the number of characters in the first string. So we'll have a row for each character, A, D, C, B, and we'll have a column for each character in the second string. In this case, it actually doesn't matter which string we make the row and which string we make the column. You can honestly know that without knowing much about the solution, just by knowing that we're given two strings. We don't necessarily know anything about the two strings, so we can't necessarily know which one to put in the row and which one to put in the column. But there is a slight optimization we can make that we'll talk about later on. But for now, just understanding this solution is complicated actually. Even though the code is quite short, that doesn't mean it's simple to understand. So you can see that in this case, I'm actually initializing the two-dimensional grid with m+1 columns and n+1 rows. So actually we have an extra row and extra column. Now every value in the grid itself is going to be 0. So we can think of that extra row being over here, and it's all zeros essentially. And we have an extra column. We can think of that as being all zeros as well. And we have this corner value as well. Why are our dimensions longer than they need to be? Well, it has to do with how we're going to have to handle some of these edge cases. If we didn't have these extra rows and extra columns, this is the general idea of how the algorithm would work. For this position, for example, we are comparing these two characters, these two C's with each other. They are equal to each other. And what we would want to put in this position is comparing the LCS between these two strings. So we're comparing these characters first, so we see that they are equal. So the value we would put here is 1 plus the result of the subproblem. The subproblem would be the LCS between these two strings. Where would the value be in that case? Well, the value, if we're computing from top left to bottom right, that value should already be computed. It should be stored in this position over here. So to get that value, we're simply going to look top left. And that's perfectly fine when you do it from this position. But when you try doing it from the top left position here, where we're just comparing these two characters, they're equal. So we say that the value we're going to put here is going to be 1 plus the value top left. Then we would end up going out of bounds. So that's why we have these extra dimensions, so that we don't get an out of bounds error. Technically, you don't need that. You could add some extra if conditions to check if we go out of bounds, but that makes the code a bit more messy. So most people prefer writing it this way. It's definitely not super simple to figure this kind of stuff out, this type of optimization, especially when you're new to dynamic programming, but I want to mention it because this is how most people will write these solutions. Also, you might be wondering, when we're comparing two substrings and then we're looking at the subproblem, in this case, we're going backwards. We're taking our, I pointer and decrementing it, and our pointer from here and then decrementing it. But when we were doing the recursive solution, we were actually doing it the opposite way. We were incrementing our pointers to get the result of the subproblem. Well, you could do it that way as well with the dynamic programming solution, but to do that, you would have to compute it from bottom right to top left. So that would basically be iterating through these loops in reverse order. I've done solutions like that before, and that's kind of how I prefer it because it's more similar to the memoization solution. So from this position, you would need to go to bottom right instead. So instead of having our extra row and column B here, we would actually have that extra row and column B in the opposite position, which is perfectly fine. But I think most people prefer going from top left to bottom right. So that's why we're doing it this way. Also, if we have our characters basically offset by 1, so normally to look at the first character, we would have our I pointer be at index 0 over here, but now we actually have it in the 1 position, and same thing with the columns. So when we're actually reading the characters, we know that the characters are stored in these two strings starting from index 0. So when we actually read the characters, we're going to be using I and J, basically our iterators, which are starting at index 0. That's perfectly fine. But when we're accessing this grid, which I've named DP, when we access the grid and we're storing the value, for example, here, we're storing the LCS between these two substrings, we want to offset it by 1. If we're at the second character, we know that this D and B are at index 1 in the input strings, but when we access the DP grid to store the value here, we're going to add 1 to DP, and we're going to add a 1 in basically both the row and the column. And we're going to do that here as well. And when we want to access, read values, if we're trying to compute the value here and this is I plus 1 and J plus 1, then to get the top left value is going to be I without the plus 1 and J without the plus 1. This is also something that's pretty abstract and confusing, especially when you don't have a picture to kind of visualize it. When you get good enough and you practice this enough and you draw pictures enough, these kind of diagrams are kind of embedded in your head so that you don't need pen and paper to practice with it. But it takes a while to get to that point, which is why I really encourage drawing this type of stuff out. It's really hard to visualize this in your head if you've never seen what it looks like on pen and paper before. But other than that, we will basically have our same DP solution. We'll go top left to bottom right. We'll compare these two characters. They are equal in this case, so we'll execute the first case where our result will be 1 plus the top left value. So the value that goes here will be 1. Here, it'll be similar, but these two characters are not equal. So we're going to get the maximum of the value to the left and the maximum of the value above. We're saying that from this problem, we're going to look at the subproblem that's this, where we skip the B character, or we're going to look at the subproblem where we skip the A character and have this substring. We know that the LCS of this is 1, so the value we're going to put here is 1. And same thing would happen over here. The LCS here would be 1. Then moving on to this position, these two characters are not equal, so we would look to the left and look up. So the value the maximum of those two is going to be 1, because remember, that's what we're doing. We're taking the maximum of these two. Same thing over here. These characters are not equal, so we would look left or look up, take the max of both of them. Well, it's going to be 1 either way. Same thing over here. It's going to be 1. Over here, same exact thing. It's going to be 1 because these two characters are not equal. Same thing over here. These characters are not equal either. Here, we finally get to a couple characters that are equal. The result here would be 1 plus the value that's to the top left, because if we know these two characters are equal, then we want to look at the subproblem AD and AB. What's the LCS between these two strings? Well, good thing we've already computed that and we put it over here. So the value that goes here is going to be 2. Here, we're going to compare A and B. They're not equal. We're going to look left and we're going to look up. The max is 1. Here, these two characters, B, are actually equal. So we're going to take 1 plus the value to the top left, and we're going to get a 2 over here. Now, finally, for the result value, we're going to have B and C, they're not equal. So we're going to look left and look up, take the max of those two, it's 2. So we put a 2 here. So this tells us the LCS between these two strings is going to be 2. So that's what we're going to return here. Now, an optimization that you might have noticed is if in the worst case, we're only looking one row up or one row to the left, or maybe top left, do we really need to have the entire grid in memory? Basically, by the time we get to the second row, we don't need this row in memory anymore. By the time we get to this row, we don't need this row in memory anymore. We just need 2 rows in memory at a time, because the current row that we're computing, we only need to look at the previous row. We never need to look 2 rows back or 3 rows back or anything like that. So we can optimize this to actually instead of the memory complexity, instead of being n times m, it can just be big O of n. Or we could actually make it big O of m. We can basically choose which one of these dimensions we want to use. Since it doesn't really make a difference which orientation we put this grid, we can do it either way. So taking the most optimized solution, it would be pretty similar to the previous solution we were looking at, but in this case, we're going to have at most 2 rows at a time. So we're going to have our initial DP row. That's going to basically be all zeros. It's going to be m plus 1 though. So we are still going to have that dummy value in the 0th position. Then we're going to basically iterate over the array, same as we did before. We're going to have our current rows. So in this case, we would have this row allocated in memory. We're going to go value by value, computing the value that goes in each position, same as we did before. But after we're done computing this row, for example, we would then initialize DP to be over here. This would go out of memory and our current row would be over here. So then we would have these 2 rows in memory, and then of course our DP would be shifted to down here. This would go out of memory, then we'd have these 2 in memory, and we'd basically keep going like that until we finally compute the last row, in which case we would return the last value of the last row. So in this case, we kind of lucked out, because if we only have 1 or 2 rows in memory at a time, we would prefer to choose the string that has a smaller size and then use that as our row. In this case, we kind of lucked out. The way we did it, we ended up choosing the string with a smaller size. So since with this code, I'm choosing the second string every time, this is our space complexity. But we could intelligently pick the string that has a smaller length and then use that as our row. I think it's a pretty small optimization. Most likely you wouldn't be required to do that in an interview, but that would change the memory complexity from being by picking an arbitrary length of one of the 2 strings. It would actually be the minimum of the length of those 2 strings. So the minimum of n and m in this case. Try to figure out how you could modify this code to get that solution. There's a pretty elegant way to do it actually, though it's difficult to come up with, so you might be able to come up with a more traditional approach, but feel free to post about this on the Discord if you're curious. Even though this problem is difficult, the good thing is if you can solve this problem, there's several other problems that are almost exactly the same that you'll also be able to solve.